Welcome to Wiki. This week is all about vector spaces and how to manipulate word vectors. Learning how word vectors are represented in natural language processing is fundamental to all NLP applications, because any NLP model you build has a first step which entails representing the word into some type of numerical encoding. For example, you can represent a word as a number or as a vector. In this week, you will also learn how to compare different word vectors through two different methods, known as Euclidean distance and cosine similarity. Furthermore, you can also plot word vectors with very high dimensions in a 2D plane to see how similar words end up clustering near one another. Jonas will show you the details.
Okay, great. Let's do it. Last week, you learned about a classification algorithm known as naive Bayes. This week, you're going to learn about vector spaces, and specifically, you will learn what type of information these vectors could encode. You'll see different types of applications that you can use with these vector spaces, and you'll see different types of algorithms you'll be implementing. Let's take a look at an example.
In this video, I'm going to introduce you to the general idea behind vector space models. You're going to see their advantages, along with some of their applications in natural language processing. So suppose you have two questions. The first one is, where are you heading? And the second one is, where are you from? These sentences have identical words, except for the last ones. However, they both have a different meaning. On the other hand, say you have two more questions whose words are completely different, but both sentences mean the same thing. Vector space models will help you identify whether the first pair of questions or the second pair are similar in meaning even if they do not share the same words. They can be used to identify similarity for question answering, paraphrasing, and summarization. Vector space models will also allow you to capture dependencies between words. Consider this sentence. You eat cereal from a bowl. Here, you can see that the word cereal and the word bowl are related. Now, let's look at this other sentence. You buy something and someone else sells it. So, what it's saying is that someone sells something because someone else buys it. The second half of the sentence is dependent on the first half. With vector space models, you will be able to capture this and many other types of relationships among different sets of words. Vector space models are used in information extraction to answer questions in the style of who, what, where, how, and etc. In machine translation and in chatbots programming. They're also used in many other applications. As a final thought, I'd like to share with you this quote from John Firth, a famous English linguist. You shall know a word by the company it keeps. This is one of the most fundamental concepts in NLP. When using vector space models, the way that representations are made is by identifying the context around each word in the text, and this captures the relative meaning. To recap, vector space models allow you to represent words and documents as vectors. This captures the relative meaning.
You learned about vector space models, and you have seen different types of applications where these vector space models are used. In the next video, you will build them from scratch, and specifically, you will see how they are built using co-occurrence matrices. In this video, you will learn how you can construct your vectors based off a co-occurrence matrix. Specifically, depending on the task you're trying to solve, you can have several possible designs. You will also see how you can encode a word or a document as a vector. Let me show you how you can do this.
To get a vector space model using a word-by-word design, you'll make a co-occurrence matrix and extract vector representations for the words in your corpus. You'll be able to get a vector space model using a word-by-document design using a similar approach. Finally, I'll show you how in a vector space you can find relationships between words and vectors, also known as their similarity. The co-occurrence of two different words is the number of times that they appear in your corpus together within a certain word distance, k. For instance, suppose that your corpus has the following two sentences. The row of the co-occurrence matrix corresponding to the word data with a k value equal to 2 would be populated with the following values. For the column corresponding to the word simple, you'd get a value equal to 2. because data and simple co-occur in the first sentence within a distance of one word, and in the second sentence within a distance of two words. The row of the co-occurrence matrix corresponding to the word data would look like this if you consider the co-occurrence with the words simple, raw, like, and die. In this case, the vector representation of the word data would be equal to 2, 1, 1, 0. With a word-by-word design, you can get a representation with n entries, with n between 1 and the size of your entire vocabulary. For a word-by-document design, the process is quite similar. In this case, you'll count the times that words from your vocabulary appear in documents that belong to specific categories. For instance, you could have a corpus consisting of documents between different topics, like entertainment, economy, and machine learning. Here, you'd have to count the number of times that your words appear on the documents that belong to each of the three categories. In this example, suppose that the word data appears 500 times in documents from your corpus related to entertainment, 6,620 times in economy documents, and 9,320 in documents related to machine learning. The word film appears in each document category 7,000, 4,000, and 1,000 times respectively. Can you get a sense of where this is going already? Once you've constructed the representations for multiple sets of documents or words, you'll get your vector space. Let's take the matrix from the last example. Here, you could take a representation for the words data and film from the rows of the table. However, I'll take the representation for every category of documents by looking at the columns. So the vector space will have two dimensions, the number of times that the words data and film appear on the type of document. For the entertainment corpus, you'd have the following vector representation. This one for the economy category, and that for the machine learning category. Note that in this space, it is easy to see that the economy and machine learning documents are much more similar than they are to the entertainment category. Coming up soon, you'll make comparisons between vector representations using the cosine similarity and the Euclidean distance in order to get the angle and distance between them. So far, you've seen how to get vector spaces by two different designs, word by word and word by document, by either counting the co-occurrence of words or the co-occurrence of words in the documents corpora. I also showed you that in vector spaces, you can determine relationships between types of documents, like similarity.
Now you're becoming more and more familiar with these vector spaces. You've seen several possible designs that you can use to solve a specific task. You've also seen how you can encode words or tweets as vectors. In the next video, you'll learn about a new similarity metric that will allow you to compare these two vectors. The similarity metric is known as the Euclidean distance. Hello! In this video, you're going to learn about Euclidean distance, which is a similarity metric. This metric allows you to identify how far 2 points or two vectors are apart from each other.
During this segment, you'll get the Euclidean distance between two document vectors, like the ones from the previous video, and then generalize that notion to vector spaces in higher dimensions. Let's use two of the corpora vectors you saw previously. Remember, in that example, there were two dimensions, the number of times that the word data and the word film appeared in the corpus. Corpus A will be the entertainment corpus, and corpus B will be the machine learning corpus. Now let's represent those vectors as points in the vector space. The Euclidean distance is the length of the straight line segment connecting them. To get that value, you should use the following formula. The first term is their horizontal distance squared, and the second term is their vertical distance squared. As you see, this formula is an example of the Pythagorean theorem. If you solve for each of the terms in the equation, you should arrive at this expression. And at last, get a Euclidean distance approximately equal to 10,667. Feel free to pause the video and check this process. When you have higher dimensions, the Euclidean distance is not much more difficult. Let's walk through an example using the following co-occurrence matrix. Suppose that you want to know the Euclidean distance between the vector v of the word ice cream and the vector representation w of the word boba. To start, you need to get the difference between each of their dimensions. Square those differences, sum them up, and then get the square roots of your result. This process is the generalization of the one from the last slide. This is the formula that you would use to get the Euclidean distance between vector representations on an n-dimensional vector space. If you remember from algebra, this formula is known as the norm of the difference between the vectors that you are comparing. Let's take a look at the implementation of the Euclidean distance in Python. If you have two vector representations like the ones from the previous example, you can use the leanalg module from NumPy to get the norm of the difference between them. If you implement this code in Python, you should get this result. The norm function works for n-dimensional spaces. The primary takeaways here are that the Euclidean distance is basically the length of the straight line that connects two vectors, and that to get the Euclidean distance, you have to calculate the norm of the difference between the vectors that you are comparing. By using this metric, you can get a sense of how similar two documents or words are.
Now that you have learned Euclidean distance, in the next video, I'll show you a different type of similarity function. Concretely, I'll show you the cosine similarity function, which is one of the most popular similarity functions. See you in the next video. In this video, you're going to learn about cosine similarity, which is another type of similarity function. It basically makes use of the cosine of the angle between two vectors, and based off that, it tells you whether two vectors are close or not.
In this section, you will see the problem of using Euclidean distance, especially when comparing vector representations of documents or corpora, and how the cosine similarity metric could help you overcome that problem. To illustrate how the Euclidean distance might be problematic, let's take the following example. Suppose that you are in a vector space where the corpora are represented by the occurrence of the words disease and eggs. Here's the representation of a food corpus, an agriculture corpus, and a history corpus. Each one of these corpora have text related to that subject. But you know that the word totals in the corpora differ from one another. In fact, the agriculture and the history corpus have a similar number of words, while the food corpus has a relatively small number. Let's define the Euclidean distance between the food and the agriculture corpus as d1, and let the Euclidean distance between the agriculture and the history corpus be d2. As you can see, the distance d2 is smaller than the distance d1, which would suggest that the agriculture and history corpora are more similar than the agriculture and food corpora. Another common method for determining the similarity between vectors is computing the cosine of their inner angle. If the angle is small, the cosine would be close to 1, and as the angle approaches 90 degrees, the cosine approaches 0. As you can see here, the angle alpha between food and agriculture is smaller than the angle beta between agriculture and history. In this particular case, the cosine of those angles is a better proxy of similarity between these vector representations than their Euclidean distance. Now you're familiar with the main intuition behind the use of the cosine similarity as a metric to compare the similarity between two vector representations. Remember that the main advantage of this metric over the Euclidean distance is that it isn't biased by the size difference between the representations. Soon, you'll get the chance to actually calculate this metric.
In this video, you learned why the cosine similarity metric is useful. If you have two documents of very different sizes, then taking the Euclidean distance is not ideal. The cosine similarity uses the angle between the documents and is thus not dependent on the size of the corpuses. In this video, you will learn how to compute the dot products between two vectors and how to compute the norm. Once you know how to do these two things, you'll be able to compute the cosine similarity score.
Now that you have the intuition behind the use of cosine of the angle between two vector representations as a similarity metric, I'll go deeper into an explanation. And then, show you how to calculate the cosine similarity metric. In this section, you will get the cosine of the inner angle of two vectors. Then, I'll show you how the value of the cosine similarity is related to the similarity of the directions of two vectors. First, you have to recall some definitions from algebra. The norm of a vector, or its magnitude, is written like this. It's defined to be the square root of the sum of its elements squared. The dot product between two vectors is the sum of the products between their elements in each dimension of the vector space. Let's take another look at two of the corpora from the last section. Remember that in this example, you have a vector space where the representation of the corpora is given by the number of occurrences of the words disease and eggs. The angle between those vector representations is denoted by beta. The agriculture corpus is represented by the vector v, and the history corpus is going to be vector w. The dot product between those vectors is defined as follows. From this equation, you see that the cosine of the angle beta is equal to the dot product between the vectors divided by the product of the two norms. Replacing the actual values from the vector representations should give you this expression. In the numerator, you have the product between the occurrences of the words disease and eggs, and in the denominator, you have the product between the norm of the vector representations of the agriculture and history corpora. Ultimately, you should get a cosine similarity of 0.87. Feel free to pause and do the calculations yourself. But what does this metric tell you about the similarity of two different vectors? Consider when two vectors are orthogonal. In the vector spaces that you know so far, it is only possible to have positive values for any dimension. So the maximum angle between pair of vectors is 90 degrees. In that case, the cosine would be equal to 0. And it would mean that the two vectors have orthogonal directions, or that they are maximally dissimilar. Now let's look at the case where the vectors have the same direction. In this case, the angle between them is 0 degrees, and the cosine is equal to 1, because cosine of 0 is just 1. As you can see, as the cosine of the angle between two vectors approaches 1, the closer their directions are. Now you know how to get the cosine similarity between any pair of vectors. An important takeaway is that this metric is proportional to the similarity between the directions of the vectors that you are comparing, and that for the vector spaces you've seen so far, the cosine similarity takes values between 0 and 1.
To recap, you have learned to compute the cosine similarity score between two vectors. For the positive vectors you have seen so far, the score is bounded between 0 and 1. Note that if you were to take the cosine similarity score of a vector with itself, you will get 1. If the vectors are perpendicular, it will give you 0. So similar vectors have higher scores. Hello! In this video, you're going to learn to manipulate vectors by performing some simple vector arithmetic, meaning by adding vectors or subtracting vectors, you'll be able to predict the countries of certain capitals. Let's dive in.
I'll show you how to manipulate vector representations in order to infer unknown relations among words. Suppose that you have a vector space with countries and their capital cities. You know that the capital of the United States is Washington, D.C. And you don't know the capital of Russia, but you'd like to use the known relationship between Washington, D.C. and the USA to figure it out. For that, you'll just use some simple vector algebra. For this example, you are in a hypothetical two-dimensional vector space that has different representations for different countries and capital cities. First, you will have to find the relationship between the Washington, D.C. and USA vector representations. In other words, which vector connects them. To do that, get the difference between the two vectors. The values from that will tell you how many units on each dimension you should move in order to find a country's capital in that vector space. So to find the capital city of Russia, you'll have to sum its vector representation with the vector that you also got in the last step. At the end, you should deduce that the capital of Russia has a vector representation of 10, 4. However, there are no cities with that representation. So you'll have to take the one that is the most similar to it by comparing each vector with the Euclidean distances or cosine similarities. In this case, the vector representation that is closest to the point 10, 4 is the one for Moscow. Using this simple process, you could have predicted the capital of Russia if you knew the capital of the USA. The only catch here is that you need a vector space where the representations capture the relative meaning of words. Now you have a simple process to get unknown relationships between words by the use of known relationships between others. You now know the importance of having vector spaces where the representations of words capture the relative meaning in natural language. In upcoming parts of this specialization, you will perform more sophisticated tasks taking advantage of this type of representation.
You have now seen a clustering of all vectors when plotted on two axes. You have also seen that the vectors of the words that occur in similar places in the sentence will be encoded in a similar way. You can take advantage of this type of consistency encoding to identify patterns. For example, if you have the word doctor, and you are to find the closest words that are closest to it by computing cosine similarity, you might get the word doctors, nurse, cardiologist, surgeon, etc. In the next video, you will learn how to plot these d-dimensional vectors on a 2D plane. It is often the case that you'll end up having vectors in very high dimensions. You want to find a way to reduce the dimension of these vectors to 2 dimensions so you can plot it on an xy axis. You will now learn about principal component analysis, which will allow you to do so.
You are going to be using principal component analysis to visualize vector representations with higher dimensions than the ones that you've seen plotted so far. To get started, I'll give you some intuition on the motivation for visualizing vector representation of words, and you'll see for yourself what principal component analysis does and how it is used for dimensionality reduction. Imagine you have the following representation for your words in a vector space. In this scenario, your vector space dimension is higher than 2. You know that the words oil and gas and city and town are related, and you want to see if that relationship is captured by the representation of your words. So, how could you visualize your words in order to see this and other possible relationships? Dimensionality reduction is a perfect choice for this task. When you have a representation of your words in a high dimensional space, you could use an algorithm like PCA to get a representation on a vector space with fewer dimensions. If you want to visualize your data, you can get a reduced representation with 3 or fewer features. If you perform principal component analysis on your data and get a 2-dimensional representation, you can then plot a visual of your words. In this case, you might find that your initial representation captured the relationship between the words oil and gas, and city and town, because in your 2-dimensional space they appear to be clustered with related words. You can even find other relationships among your words that you didn't expect, which is a fun and useful possibility. Now that you know what PCA can help you achieve, let's go into detail on how it works. For the sake of simplicity, I'll begin with a 2-dimensional vector space. Say that you want your data to be represented by one feature instead. Using PCA, first you'll find a set of uncorrelated features, and then project your data to a 1-dimensional space, trying to retain as much information as possible. As you can see, this process is quite straightforward. Coming up, you'll see for yourself the details of how this algorithm works. Along with how to get uncorrelated features, you'll also project your data for a representation in a lower dimension while retaining as much information as possible. Let's do a quick review before you go. PCA is an algorithm used for dimensionality reduction that can find uncorrelated features for your data. It's very helpful for visualizing your data to check if your representation is capturing relationships among words.
You learned how to visualize components using PCA. So given any d-dimensional vector, you can transform it into 2 dimensions and then you can create a plot. In the next video, we will go over how the algorithm actually works. You will now learn about eigenvalues and eigenvectors, and you will see how you can use them to reduce the dimension of your features.
First, I'll show you how to get uncorrelated features for your data. and then how to reduce the dimensions of your word representations while trying to keep as much information as possible from your original embedding. To perform dimensionality reduction using PCA, begin with your original vector space. Then, you get uncorrelated features for your data. And finally, you project your data to a number of desired features that retain the most information. You may recall from algebra that matrices have eigenvectors and eigenvalues. You do not need to remember how to get those right now, but you should keep in mind that in PCA, they are useful because the eigenvectors of the covariance matrix from your data, they give directions of uncorrelated features, and the eigenvalues are the variance of your datasets in each of those new features. So to perform PCA, you will need to get the eigenvectors and eigenvalues from the covariance matrix of your data. The first step is to get a set of uncorrelated features. For this step, you'll normalize your data. Then, get the covariance matrix, and finally perform a singular value decomposition to get a set of 3 matrices. The first of those matrices contain the eigenvectors stacked column-wise, and the second one has the eigenvalues on the diagonal. The singular vector decomposition is already implemented in many programming libraries, so you don't have to worry about how it works. The next step is to project your data to a new set of features. You will be using the eigenvectors and eigenvalues in this step. Let's denote the eigenvectors with U and the eigenvalues with S. First, you will perform the dot products between the matrix containing your word embeddings and the first n columns of the U matrix, where n equals the number of dimensions that you want to have at the end. For visualization, it's common practice to have 2 dimensions. Then, you'll get the percentage of variance retained in the new vector space. As an important side note, your eigenvectors and eigenvalues should be organized according to the eigenvalues in descending order. This condition will ensure that you retain as much information as possible from your original embedding. However, most libraries order those matrices for you. Wrapping up, eigenvectors from the covariance matrix of your normalized data give the directions of uncorrelated features. The eigenvalues associated with those eigenvectors tell you the variance of your data on those features. The dot products between your word embeddings and the matrix of eigenvectors will project your data onto a new vector space of the dimension that you choose. You are now ready to implement PCA in this week's assignment to visualize word representations. Good luck with that, and remember to have fun.
Congratulations! You now know all about PCA and you know all the steps required for you to implement it. Next week, you will learn about vector spaces, and I'll show you how you can use them to build a simple machine translation system.
Great work getting through this week's materials. You now know what vector spaces are, how we represent words as vectors, and how to manipulate them. For example, you saw how to compare 2 words by doing cosine similarity or Euclidean distance, and you learned why cosine similarity is more common. In this week's programming assignment, you will be given capital cities and their countries in word vectors, and you will manipulate them by finding the country given a capital city. Isn't that cool? You will also reduce high-dimension word vectors into 2 dimensions and plot them on an xy plane. You will find that similar word vectors end up being clustered near one another. Next week, you'll get started on machine translation. Good luck in the programming assignment.